Welcome back. So the next component of cost estimation that we want to talk about is something called learning curves. And learning curves are kind of a special topic in the sense that it's a way we can evaluate things that we've done before and have gotten better at. And typically when we get better at things, we also get faster at doing some things. And of course, when you're doing estimation, time is money. This is why we talk about learning curves. So let's get started. So what makes a learning curve work in our favor? Well, research has shown that, and you probably even know this intuitively, as you do something over and over again, you get better at it. As you iterate, this activity gets faster. Sometimes the quality goes up because you get better at it. And that's part of how we learn and how we perform over time. So we can actually encompass that in a little bit of an equation to help account for that when we're going to do, say, several projects back to back to back that are very much the same. Now again, the caveat to this type of estimation or using this type of theory is that the project or what you're going to do is so close to something you've already done that it's like you've been doing it before. And so you get faster and faster and faster at it. So oftentimes we look at the doubling of an output because we get better at it. And so it costs us less in time, thus less in money. Note, there's always a limit. You're never going to decrease your time down to zero because there's always at least a minimum. So we usually have something that plateaus about a low range where you just can't really do it much faster unless there's a massive method change. So an overall equation that we can use as a very decent estimate is the learning curve, which is y as a function of x, and x is the number of iterations that we've done this sort of thing. So it's the time for a unit of output. Now again, each unit is a repetitive time that we've done something. So x is the number of units of a project, of a product, whatever it is that we're outputting. A is the amount of time it takes for that very first time. And remember, the very first time you do anything, as we all know with practice, it takes you the longest amount of time to do that. My wife and I have been remodeling a bathroom, and let me tell you, the first day we were trying to do tile, it was taking us forever because we'd botch up the cutting of the tile and all these kinds of things, just trying to do it for the first time. Then we have the exponent b, which is what we call the learning curve slope. The learning curve slope simply is calculated as the log of the decimal version of our learning rate divided by the log of 2, which is really just a constant number. So the decimal learning rate can be anything from like 70%, 90%, 85%, 65%. You can look at it from a percentage standpoint, but when you put it into this calculation, you convert it to a decimal. So if I was going to say it's 70%, I'd put in 0.70. Take the log of 0.70 divided by the log of 2. That would be in the exponent. So just keep that in mind when you're running these calculations. So this equation you can do for any number of units. And then if you want to calculate all of the units, you would add up the time for all of them. We'll take a look at that. The other alternative that you can do for this calculation is using learning curve coefficient tables. In the latest version of the book, I think it's page 302. It's different pages in different books, but it's usually in the area where there's the homework problems. They have a table in here, but you can also find learning curve coefficient tables online. They're actually freely published, so you can find those. And it gives you a little bit of a different equation of the time to do the nth activity, or the number of times you've done it, is equal to the time it took you the first time times x to the b, which that's the same equation. So what we've changed here is, you notice t1 as replacing a. So it's a different format. And instead of using x on the left-hand side, they use t sub n. And then really what they do is, since if we have a specific learning coefficient, say it's 70% again, that value of b will be fixed for any number of units. And so it's only going to change by x on which term we're doing it. So if we combine those things, you can get a coefficient and they can calculate the whole table before you ever have to do anything. So it's really kind of looking up the value depending upon which unit you're at. However, you then are limited to by whatever is listed on the table. Like I think the table in the book goes like every 5. So, but if you're trying to do 7, you're not going to be able to calculate that with a table that doesn't show you the 7th iteration. So keep that in mind, but it's a very useful tool to shortcut the calculation. So let's say we're using the full calculation. Here we have a design engineer, wants to create 5 alternatives, but they're going to be very similar 3D printed models. Pay rate, $40 an hour, overhead 60%, takes about 40 hours the first time. So what we think is the linear estimate if we don't have a learning curve. Well, I would say take his rate, multiply by 5 units, multiply by overhead, number of hours per unit, and we're going to estimate $12,800. Now, is that high or is that low? Well, if the engineer is not learning anything each time they do it, then it might be accurate, but chances are that engineer has been learning as they've been going. If they're learning as they're going, they're going to get faster and faster with the 2nd through 5th units. So that cost would actually be fairly high, or probably extremely conservative, which you can do that. You can have an extremely conservative estimate. It just depends upon how competitive the playing field is. If you're in a highly competitive industry like construction, you probably can't do that. But in other areas, you might be able to get away with it. So now let's account for that learning rate. And let's assume he has a learning rate of 80%, which ends up being 0.80. So then we plug that in for for our learning rate. So log of 0.8 divided by the log of 2, then calculates our b. Notice it's negative because we took the log of a number smaller than 1 on the numerator. That makes it a negative amount, which means our curve is going to go down. So it's a negative 0.322. Now, it's unitless. That doesn't have units next to it because it's up in the exponent. And 40 hours was the time it took him to do the first time. So we can actually calculate, actually 40 hours was the time it took them to do the 5th alternative. I always take this problem always gets me there. So that's the time it took to get the 5th alternative. So we actually have to back calculate the time it took them to do the 1st alternative, which is kind of weird. That isn't normal. You'd normally know the first time and then you're trying to calculate the 5th time the other way around. But that's fine. It's an example. So we calculate A here, which is the first time. So we divide the 40 hours for the 5th time, divide it by 5 to the negative 0.322, which is 0.596, and then we get 67.16 hours. So that is actually the initial amount of time it took them the first time to do it. So if we were estimating what it took them to do the 5th time, because it's the 5th time, not the first time, that's actually an underestimate. Okay, so if we know that's the initial time, 67.16 hours, maybe we want to calculate what's the total time it took them to go through iterations 1 through 4 and iteration 5. So we can set A equal to 1, set the iteration number from 1, 2, 3, and 4. And when we do this, we can solve for the y values. And so notice the exponent hasn't changed at all. It's the same. The only thing that's changing is that x value. So here we have the x value of 1, 2, 3, 4. They all just get to a different exponent, and so we get these numbers here. We get a value of 1 again, because 1 to the anything is 1, and so on, 0.799, 0.702, and 0.639. Now, if we want to figure out the multiplier, we say, okay, well, now we got to add all these up, 1, 0.799, 0.702, 0.639. That gives us a value of 3.14, almost sounds like pi. Then we multiply that times the very first time, that's 67.16 hours. We get a value of 211 hours. Now notice, we only just did this for 1 through 4. Why they didn't do it for 5, they could have. We could have just calculated 5 to the negative 0.322, but we've already done that before. So we knew it was 40 hours. So we're just going to add those 40 hours, having already calculated that, to the 211, and we get 251 hours, roughly. Now, that's the amount of time, but remember, we have to figure out cost. So now we have to go back and calculate cost based upon that time. So just when you figured out the time, you're not done yet. You then have to go back and calculate cost. If we want fully loaded labor costs, we include our overhead and then the rate, $40 an hour. Multiply by that time, we get a value of $16,065 from there. Remember, you also have the alternative. You can use the learning curve coefficient table. Look it up online. Use it on page 302. You decide which way you want to do that. So what does that look like mathematically on a graph? Well, this is what it looks like. It starts with your time and cost being significantly high the first time. So it's wherever you start, which actually they should plot. If we were plotting the 67 hours, it should be plotted up here. And as you go on and on, oh, this is actually a different graph altogether. Because if you notice, this doesn't plateau at 5 iterations, would have been here. This is actually getting around steady state around 100 iterations. So this is a completely different equation. So the way we can assume steady state is kind of how we always assume steady state with a first order system, where values are within plus or minus 2%, and they don't go outside of that range. They stay within that range. So whenever you reach that, that's kind of what we'd consider steady state. But this is kind of the curve you'd expect. And again, you won't ever get exactly to 0. There will always be an offset. So what are some problems with different types of cost estimation? Well, we can have low initial estimates because maybe we're not entirely sure or don't have the experience about everything that's required. So oftentimes you'll see this as lowball or scope was misunderstood. And so people just do it so they can get the project, and now all of a sudden they have a tiger by the tail and it's bigger than they thought. Maybe there's a lack of definition. Requirements weren't nailed down. So if you notice, I have the little bullseye sign kind of off. They didn't quite have the goals defined well. The purpose wasn't quite right, so they're not quite there. Maybe we have some technical difficulties. Things aren't working the way they should. Just like originally when the Boeing V-22 Osprey, the tilt rotators weren't working quite right. Then there's specification changes. I like to show a changing table with a baby because it just reminds me of changes when I had to change my kids. Pretty funny. But you get scope creep. Things change, and now all of a sudden your client wants different things, or they want new features. They want these other things they didn't think of before. So the problem with that is if you have a fixed quote, now it's on you. However, if you have a time and materials quotation, say, well, look, that's great. We can change those things. This is how much more time it's going to be, and this is how much more cost it's going to be to add those things. So that's really what you want to do when you're dealing with those kind of situations. Different external factors, things that you can't account for. So COVID, nobody accounted for that, I assure you. Inflation, economic factors, war, politics, acts of nature, tornadoes, anything like that can blow cost out of proportion, totally change things. So when we're talking about software project estimations, things are a little bit different. There's a couple different things that we have to look at. So I always like some of these Dilbert cartoons because they always kind of get to the point in a funny way. So your user requirements include 400 features. Do you realize that no human will be able to use a product with that level of complexity? Good point. I better add easy to use to the list. So he adds another feature. So, but it's absolutely true. The complexity of the software not only affects users, but it also affects the project. And so there's been some schools of thought that have done analyses and trying to do estimations of software projects based upon those complexities, or more specifically what they call function points. So it's kind of a standard unit of measure that represents the function size of any software application. Now, they say that, but it's typically when you're talking about line-by-line coding. There's also graphical coding, which is a little bit different because you can't do line-by-line. It's based upon icons and different things that you plug in. Okay, so typically from a user standpoint, it's a process for estimating size and cost of the software using a functional point analysis. Let's take a look at what that is. The reason it's important, however, is depending upon the number of lines of code or the software size, you're going to be spending development time doing different things. So if you notice on this graph, the smaller the software, the more you're going to be spending on unit testing, coding debugging, and some detailed design. Much less on system testing, integration, or architecture. But as it gets larger and larger and larger, more complex, then you'll be spending a substantially larger amount of time on system testing, integration, and architecture as it gets bigger and bigger. Okay, so but what is a function point analysis? Well, it's number of inputs, number of outputs, number of interfaces, number of queries, and number of files involved. From those 5 things, we can then have multipliers to try to estimate our time that's going to be required. So they have different complexity weightings. So each of these you have to categorize. Say for the number of inputs, is this a low number of inputs? Is this a medium number of inputs? Or is this a high number of inputs relative to other things that we've seen? Same with outputs. Is it low, medium, or high? Number of files, low, medium, or high. Each one of these, you basically check what that is, and then what your multiplier is for each of these things. Notice the higher the complexity, the higher the multipliers go. So for example, number of queries goes from 5 to 10x to 15x. So it gets substantially larger. So let's see an example of how this is used. So let's say number of inputs, we have 4 inputs. And that's kind of a medium level of complexity, so we multiply it by 15. We have 10 outputs, multiply that by 20. We have 3 interfaces, which is low, multiplied by the 3. Number of inquiries, we have 10. 6 times 10. I think I just said the other ways. I did. Sorry, we have 15 inputs, 20 outputs, 3 interfaces. I was reading the numbers on the left. 6 inquiries, and then 40 different files that we're dealing with. So when you multiply all those together, you get totals for each of these things. Then you add all those totals in the right-hand column. We get a number of 409 function points. So that's what those are. Then the question is, how many function points can a person, a programmer, reliably build in a month? That depends completely upon your programmers. It depends on your programming house, how much you can put out. Examples in the book shows like 10 per month. We're using an example of 20 function points per month here. Could be 5 function points. That's really kind of the subjectivity in here as to what is an acceptable value for function points. And it also depends upon the skill level of the programmers, obviously. So in this case, we're assuming 20 function points per person month. So we have 409 function points divided by 20 function points per month. Function points cancels, months goes on top, you get 20.45 months. Now then you have to multiply those months times the cost per, if that's a programmer per month, or the average of your group of programmers. So say they're getting paid $8,000 a month. We multiply that out, then the software project estimate is going to be $163,600. And that's for almost 2 years of work, just shy, 1/4 shy of that. So, and that's essentially the function point analysis on that. Okay, so we've covered 2 different things really, the learning curve and we've covered function point calculations. And that's it for this video. The next video will go on to creating a budget. Thank you.